Welcome back to the part 2 for the topic of the area under the curve. And now we're going to do examples so that you understand what we just introduced to you using all those areas, ideas of the estimation, and a weird notation for the Riemann sums. So I give you a graph and I tell you, hey, find the area under this graph. Can you do that? Well, first of all, let's give you more details. Find the area under the graph with the given expression, the function y equals x squared plus 1, and on the given interval, or else the area will be infinite because these parabolas keep growing forever. So I cannot ask you to find the area forever. Actually, I will ask you that later when we learn integrals and limits at the same time. But that's going to be probably in Calculus 2 class. For now, we're working on the closed interval from 0 to 2. Here it is, from 0 to 2. So I don't care about anything outside of this part, somewhere like this. And I want to know what is the area below only this part. So I can be drawing this forever, but you got it. I will try to be fast. Done. So this is what I need to find, this area. How can you do it? Very interesting question, you know? Like, we're teaching students to find areas since schools. You know, the area of the triangle, of the circle, even you can Google the area of the ellipse and so on. And kind of we never actually told you, so what happens if we don't have a nice shape like rectangle, circle, triangle, and so on? What would you do? And this is a pretty cool idea that we can just take like little toys, put many rectangles everywhere, and since we know the areas of rectangles, this will give you a nice approximation of the area with the shape which we don't know. And that's a pretty cool idea from the engineering point of view, right? Like how to know the area of the wall if it has this type of shape. Well, from the definition we gave you, we're going to decide how many intervals we want to have, or we want to how many rectangles we're going to use. And we're just deciding here as a computer scientist that codes this problem, or as an engineer that set up this problem, or mathematician, I can decide. But in your homework, we will tell you, use 4 rectangles, using n equals 4 rectangles to approximate this area under the graph. Okay, the whole area called S, then S will be a sum of, well, it's not going to be exact, right? It will be approximated, underestimation or overestimation, depends on the situation, S1, S2, S3, and S4. Those will be different rectangles, or even you can call them strips if you want. You will see it in the book sometimes. Strips. Different strips with the same base. So these rectangles, we're going to have the same. They will have the same fixed base. That's very convenient. And we're going to call it delta x. And they will, but all different heights. But different heights. Because the function is not constant. That's the same, that's the whole point. If the function would be constant, like we had an example in the previous video, then we don't have to approximate the area. It will be exact rectangle, base times height. But since the height is different, then we need to have more different, divergent, I would even say, rectangles to approximate the area in the situation. Let's do it. So steps. Step 1, divide in your interval, divide the interval from 0 to 4 by 4. Why by 4? Because we're going to have 4 rectangles with the same base. So how to do that? The formula is delta x. There was a formula in a definition over here. The formula is, where is it? Probably a different one. Oh, here it is. Delta x is b minus a over n. B and a are given, And n, either you decide on it or it is given. B minus A over n. That's going to be my step size. Step size also. You will see this phrase quite a lot, step size. So it's going to be 2 minus 0 over 4. 2 minus 0 are B and A. 4 is the number of rectangles we chose to have, and the result is 1/2. This is the base of each rectangle. That's why we call it delta x, the step size. So 1/2, it means we need to divide this interval by 2 and this interval by 2, and we're going to have 4 intervals, 1/2 over here, and then one more 1/2, one more 1/2, and so on. 1/2, and so on. There's going to be 3/2, right, or 1.5, and then 2. So now we're going to be building rectangles. But what kind of rectangles? We just told you that they can be right endpoint, they can be midpoint, or they can be left endpoint. And we're going to do all 3 cases for you right now to know how to proceed with your homework. Now, let's do A. Let's first use right endpoints. Right endpoints. And you will see that the answer will be different depending on the method you choose. Right endpoints method will look like this. To create rectangles, we use right endpoint to define the height of the rectangle. So choose this point over here, ignore the beginning, ignore the 0. Start with the second point. Go up, reach the graph, go to the left. Next one, go up, reach the graph, go to the left. Next one, go up, reach the graph. And the last point, go up. Wow, that's a huge piece outside. Looks like it's going to be overestimation, right? Overestimation over here because too many extra pieces show up. And also interesting thing that we skipped the beginning. That's important for calculations. So I will point this up. Skip x sub 0, the first point. We always skip it because we keep touching with right rectangles. So we're going to call it R sub 4. R sub 4. Do we point this out before? No, actually we should. That the left one will be called L sub n. The right one will be called R sub n. And M sub n is midpoint. N will be number of rectangles we have or numbers of subintervals. So R sub 4 will be my area using those 4 rectangles. Well, each rectangle, look at this graph over here. Each rectangle has base 1/2, right? Then it's going to be 1/2 base times the height. 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 4 of them. That's not usually how people write it down. People usually factor out the same base. That's the whole point of having the same base. You can factor it out and then just add all the heights over here. How to find the height? Let's see. The height for this point, the height for the first rectangle comes from the right point touching the function. The right point is 1/2. So I'm taking this 1/2 and plugging it into y equals x squared plus 1. So basically it's going to be f at 1/2. You see we skipped 0, reminding you. Then the next point, the next height, this rectangle is higher. That will be f at 1. So I'm going to have f at 1. Next one, basically you don't have to keep going to the graph. Just keep adding 1/2 to the numbers. F at 3/2, and then what is 3/2 plus 1/2? That's going to be 4/2. That's just 2. F at 2. So again, we skipped the first original point. We only have to have 4 rectangles. We only need to be counting second, third, fourth, and fifth point. Check it out. First point, second, third, fourth, and fifth. And we keep skipping the first one for the right end point. factoring out those points, factoring out 1/2 makes the process faster. And actually people create a table and they actually calculate if the function is, and the function is x squared plus 1, then I need to calculate f at 1/2, f at 1, f at 3/2, and f at 2. So if you code all of this, the computer does it really fast. And I'm literally plugging in 1/2 squared plus 1, that's 1.25. F of 1, that's 1 squared plus 1, that's 2. This one is 13/4. And the last one is 5, because 2 squared plus 1 is 5. And I'm plugging those numbers over here. F of 1/2 is 1.25 plus 2 plus 13/4 plus 5. Calculating the answer is 5.75. That's the estimated area. That's the estimated area using 4 right endpoint rectangles. I have the exact answer for you. So this is the table we used for calculations. But I do have actually the exact answer. Note, to compare the result, exact answer is area equals 4.6, or actually 14/3. So what did we have? We expected to have overestimation, and indeed it is overestimation, because there were too many extra pieces everywhere. That's why we expected it to be a little bit too big. So on this interval, using only 4 rectangles, the answer is not really good actually. And we call this estimation. If you subtract 5.75 minus and 4.6, the difference will be called error. Error for this concrete calculation. B. Let's speed up a little bit and do left endpoints. Left endpoints. Now you know the idea. N is still 4. Graph is still the same. I can copy it. I can use it over here. And now I'm showing you how we're gonna build from 0 to 2, 4 rectangles, so the same distances here, 1/2 and 3/2, but using left endpoint. Now we're starting from 0, hitting the function, going to the right, going down, going up, hitting the function right and down, and repeat. You see, we're never gonna use 2 as in my calculations. And what do you think? It's gonna be overestimation or underestimation? And it's gonna be underestimation because too many gaps over here. So I'm expecting to have underestimation. And to point out, this was skipped. 2 was never used as the endpoint. Let's go a little bit faster. What is going to be the formula? L sub 4 indicates we use left endpoints and 4 intervals. 1/2 is factored out already. That's the same base. Then we're starting with 0, f at 0, plus f at 1/2, plus f at 1, and plus f at 3/2, and we're never gonna use f of 2. Make sense? So because the height of each is determined by the left endpoint all the time, so we're not using the very last right point at all. Well, we have most of these calculations from the table before. We're just missing f of 0, but f of 0 is easy to calculate. I can even add it to the table. F at 0 is, since the function is x squared plus 1, that's 1. So the numbers from the table are 1 plus, and keep going. I actually don't remember them. f at 1/2 is 1.25, 1.25. f at 1 is 2. And f at 3/2 is 3/4. And the answer is 3.75. Compared with the exact answer 4.6, and indeed it is underestimation. Underestimation. Here it is. Too small. For these calculations, just to review, we used 4 underestimation using 4 rectangles with left endpoints. Left endpoints. Finally, we can finish with the midpoint method. Midpoint method will be C. And midpoint method is called this way because we're literally going to be using midpoint, and usually students actually have struggles to graph it. So I would pay attention right now how we'll create the same picture from 0 to 2 for the midpoint, knowing that this is 1/2 since we have 4 of them and 3/2. So I will take this point, I will take from 0 to 1/2. I need to have a rectangle the way that midpoint is touching the function. I will zoom in for you to see. Take the midpoint. What is the middle point from 0 to 1/2? That's 1/2 divided by 2. So that's actually not convenient because we will have to calculate this point, and it's 1/4, right? Because 1/2 divided by 2. And then go to the left and go to the right and create a rectangle. One piece will be above the graph, the other piece will be below the graph. Find the midpoint from 1/2 to 1, that's 3/4. 3/4. And you will have, you go up like this. Go to the left, you see it's above the graph. Go to the right, it's below the graph. And that's your second rectangle. Find the midpoint from 1 to 3/2. That's 5/4. Go up to the left, to the left, to the left, to the right, to the right. And you have third rectangle after singing. 7/4 will give you the last one. Remember, you're supposed to have 4 rectangles. If you have more than 4 rectangles or less than 4 rectangles, you messed up somewhere. Optimistic. But that's the best way to know, because it's supposed to have 4. This is how beautifully my 4 rectangles look like. Hopefully yours look better. Now, from now on, we're not going to be using left endpoints, right endpoints to plug into the function y equals x squared plus 1. We'll be using those midpoints, which I just found. And that's why this method is actually not very convenient, because it requires more calculation. But it gives better result. You will see it right now. So we're going to call it m sub 4. We're going to factor out 1/2. That's still the same base for each rectangle. But now the height of each rectangle comes from the midpoint. The first midpoint is f of 1/4. Then f of 3/4, then f of 5/4, and f of 7/4. And you have to create a new table now because we don't have those values. You have to calculate what is f of 1/4, which is 1/4 squared plus 1. Then the next one and the next one. So you need to find all of these, right? Create a table. Don't be lazy. And then you'll get result. And I just have result. So your job is to check it by yourself. 4.625. Let's see. The exact answer was... Note, the exact answer is 4.6. 4.6. The first answer we got was 5.75, way too big. The second answer was 3.75, way too small. And this one is 4.6, but 25 after that. That's the best approximation in this concrete example. Best approximation for y equals x squared plus 1 on 0, 2. And it makes sense because the extra pieces kind of matched with the empty pieces, see? And since they more or less matched, that approximation is really good. Not always the case, depends on concavity, how concave up, concave down the function is, and so on. So that's not always the case, just for you to know. And still, midpoint is usually one of the favorite ones when you do coding, if you don't have to calculate those numbers by hand. So that's kind of important idea. And also I wanted to point out that if you have more rectangles, I'll make a note. If we decide to have more rectangles, for example, well, can you have 100? That would be fantastic, but that would be a lot of calculations. But you can actually check that will be a lot to calculate, but still. Then the results, the approximation will be much better. And I showed you already the animation in the previous video. If you did not watch it, go ahead and watch it. That it matters how many rectangles you use. The more the better, because they shrink, so the base shrinks, and then the height fits the graph really well. And that's exactly where we're using the idea of using the limit with the making as many and infinitely many rectangles as possible. If we have infinitely many rectangles, then the area becomes perfect. And that makes sense, and that will take you to the topic of integration. Basically, we're gonna do right after that. So I will just remind later. The more rectangles we use, the better.